Hey everyone, welcome back to our explainer on Class 10 Science, Chapter 5, Periodic Classification of Elements. Now you've already completed Part 1 on Dobereiner's triads and Newland's law, and Part 2 on Mendeleev. So today we're moving on to Part 3 to conquer the modern masterpiece itself, the modern periodic table. Okay, let's just dive right into this. Mendeleev's table was a total game changer for its time and hugely successful. But scientists eventually realized it had some pretty serious limitations. So why did it ultimately hit a wall? Well, it came down to a fundamental flaw in the foundation. Arranging elements by atomic mass was simply not the correct basis for classification, and it created too many inconsistencies that chemists just couldn't ignore anymore. In 1913, a scientist named Henry Moseley provided a brilliant solution. He proposed a massive shift in thinking and defined the modern periodic law. Moseley proved that the physical and chemical properties of elements are actually periodic functions of their atomic numbers, not their mass. This meant that when you arrange elements by increasing atomic number, their properties repeat periodically and completely predictably.
Today we're taking a full tour of the elements to cover the modern periodic law, periods and groups, the element families, periodic trends, and we'll wrap it all up with a quick revision for your exams.
Let's start with Part 1, the modern periodic law.
Let's see exactly how this new law fixed the glaring anomalies in the old map. Because elements are now arranged by atomic number, everything just falls perfectly into place. For instance, all isotopes of an element logically occupy the exact same position now, since they share the same atomic number. Plus, those tricky anomalous pairs from Mendeleev's time, like cobalt and nickel or tellurium and iodine, just disappeared entirely under this new system.
Moving on to Part 2, periods and groups explained. The modern table consists of exactly 7 horizontal rows, and we call these rows periods. The first period is incredibly short, with just 2 elements, hydrogen and helium. The second and third are also considered short periods with 8 elements each. Moving down, the fourth and fifth are long periods with 18 elements, while the sixth is the longest with a massive 32 elements. Finally, the seventh period is incomplete and houses our radioactive elements.
Now intersecting those 7 rows are 18 vertical columns. We call these vertical columns groups. The absolutely crucial point here is understanding the difference between these two structural pillars. Periods are our 7 horizontal rows, stretching left to right. Groups, on the other hand, are our 18 vertical columns going up and down. The magic of a group is that elements within it have the exact same number of valence electrons. Because of this, they exhibit incredibly similar chemical properties.
Let's jump into Part 3, meet the element families.
What's really fascinating is how beautifully distinct these group families are. Over in Group 1, we have the alkali metals like lithium, sodium, and potassium. These guys are highly reactive metals. Jump all the way across the table to Group 17 and you'll find the halogens, fluorine, chlorine, bromine, and iodine, which are extremely reactive nonmetals. Right next door to them in Group 18 sit the noble gases like helium, neon, and argon. And unlike the others, these are completely chemically inactive. They're totally chill.
But wait, what about element number 1? Where in the world does hydrogen fit into this rigid structure?
Hydrogen is placed at the very top of Group 1, sitting right above the alkali metals. But honestly, it's totally unique. It's a bit of a rebel. It acts like an alkali metal sometimes, but also a bit like a halogen at other times. Because of this dual personality, its placement is a really special case in the periodic table.
All right, Part 4, understanding periodic trends.
We really need to learn the traffic rules of our map. Periodic trends show us how properties predictably change across periods and down groups. First up is valency, which is an atom's combining capacity. When you move horizontally across a period, say from lithium to neon, the valency climbs from 1 up to 4 and then drops back down to 0. It's literally like hiking up a mountain and back down. However, when you travel vertically down a group, the valency remains exactly the same. Every element in Group 1 has a valency of 1.
Next is atomic size, which is the distance from the nucleus to the outermost shell. Counterintuitively, when you look at atomic size across a period from left to right, it actually shrinks. Why? Because the increasing nuclear charge pulls the electrons tighter and closer to the center. But as you travel down a group, the atomic size grows because you're adding whole new electron shells to the atoms.
Then we have metallic character, which is the tendency of an atom to lose electrons. Across a period, this character decreases because atoms lose electrons much less easily as you move right. But travel down a group, and the metallic character strictly increases, as those larger atoms lose their outer electrons much more easily.
And as you might guess, non-metallic character, the tendency to gain electrons, is the exact mirror image. Across a horizontal period, this tendency strictly increases. Conversely, as you move down a vertical group, non-metallic character decreases.
Finally, Part 5, Quick Revision and Exams. Let's lock all this fantastic knowledge in with a rapid-fire review for your exams. First question, can you clearly state the modern periodic law? Take a second and see if you remember it.
Here's the answer. The physical and chemical properties of elements are periodic functions of their atomic numbers. Remember, atomic numbers is the absolute key phrase here that separates Moseley's modern law from Mendeleev's older version.
Question 2 for your exam prep. Why exactly are noble gases chemically inactive? We saw them earlier hanging out in group 18.
They're inactive because they have completely filled outermost valence shells. This makes them perfectly, incredibly stable, and chemically inert. They simply don't need to gain, lose, or share electrons with anyone else.
The modern periodic table gives us the ultimate systematic map to understand and predict the behavior of the universe's building blocks. It truly is one of the greatest achievements in chemistry. But it leaves us with a pretty exciting, provocative question. As our scientific technology continues to advance, what new, undiscovered elements might be added to this map in the future? Thank you so much for joining me on this explainer. Keep studying those trends and stay curious.